Welcome to the quarantine special series of talks from SICTAX at IIT Kanpur. Today we have with us Pranav Bisht to speak on polytime blackbox identity testing for sum of log-variate constant with ROABPs. Pranav is doing his PhD here at CSE IITK. He has given many offline talks in SICTAX. The first which I attended was a part of bootcamp series on algebraic complexity theory, where he talked about ROABP model in detail. Our viewers might be interested in his recent talk on lower bounds and upper bounds of ROABP, which was recorded and is available on the channel. You can find the link of the talk in the description below. Please feel free to bring your doubts and questions to the comment section below. And now I'll hand over the screen to Pranav for talk to begin. Enjoy. Over to you, Pranav.
Okay, thank you, Pratik. So let's share the screen. Wait a second, I have to do this full screen. Okay, the screen is visible, right?
Yeah.
Okay, so recording is fine.
Yeah, I guess, yeah, it seems fine.
So first of all, let's thank Pratik for taking the initiative to record and upload everything, coordinate this SICTAX talk during this quarantine. And also let's thank Professor Nitin Saxena for inspiring the SICTAX group to be active in the lockdown period also. I hope everyone is doing fine during this pandemic. Everyone is in good health. So today we will be talking about the polynomial identity testing problem, PIT problem. And the model in focus for this talk will be that of ROABPs. The full form is read once oblivious algebraic branching programs. So you can probably see this long title. So we'll be talking about specifically in the ROAP also, we'll be talking about the sum of ROAPs model. And there we will restrict the width of each ROAP to be constant, and each ROABP will be log-variate. It will number of variables will be logarithmic to the size of the ROAP. So this is joint work with Professor Nitin Saxena, who is also my advisor. So we will see every term, each will define PIT, ROAPs soon in the talk. So let's move to the next slide. So first I'll state the main results of our paper informally. So this talk is based on a recent paper which I showed that it's a joint work with me and Professor Nitin Saxena. So the first main result is that Blackbox PIT for sum of constantly many log-variate constant width ROAPs is in polynomial time. So this is a sum for those who are familiar, they can understand which model is this, but most of the audience might not be familiar, and we will no need to worry, we will be discussing each definition. We will define everything in the coming slides. So the model is sum of ROAPs, and each ROAP, the number of summands is constantly many in this case, and the width is constant, and number of variables is also logarithmic. So we'll see why all these restrictions are well justified and still the model is quite non-trivial. So we solve this model and give the polynomial time Blackbox PIT for this model. So we also solve another model. So if we keep the same previous statement, and if we say that each ROABP is also computing a homogeneous polynomial, then we can actually remove the constantly many restriction. We can say that we can consider the sum of unbounded-many ROAPs. Unbounded means it is not infinite. Unbounded just means that my number of summands is bounded by the input length. So whatever will be the input size. So don't be confused with the term unbounded. Unbounded just means it is not restricted. The parameter of number of summands is not restricted. It is bounded just by the size, which is a natural bound. So the second statement also seems very surprising, because in the first statement, the hitting set is doubly exponential in number of summands, whereas in this statement, if we restrict to homogeneous polynomials, we can talk about we get poly in number of summands. The first statement is doubly exponential in number of summands, and the second one is polynomial in number of summands. So let's dive into the initial definitions first. Let's introduce. So mainly the content of the slides will be introduction, then we'll talk about the models and what is the motivation behind all this model, what all the restrictions also, why are they well justified, and then we'll briefly talk about proof overview of the main results. Okay, so what is PIT? PIT is it is an algorithmic problem. It's asked, given a multivariate polynomial, tell whether it is identically zero or not. So what do we mean by identically zero? Identically zero means all the coefficients in the fully expanded form are zero. So the polynomial is identically zero if I expand the polynomial in its full expanded form, monomial by monomial, each coefficient is zero. So it sounds like the problem is trivial, but the catch is that the input polynomial is not given as a list of. So generally, in high school we are given polynomials as coefficient by coefficient, as a list of monomials. But in algebraic complexity, generally we are given polynomial in a compact representation. So compact by compact or succinct representation, I mean that with a small size, I can describe a polynomial which has a exponential sparsity. Sparsity means the number of monomials in the polynomials are exponentially many, and I can represent that polynomial in a compact form. So I have given 3 examples here. So these will be the 3 main models we will be touching. So first one, the most famous, is algebraic circuits. Then there is another combinatorial model, algebraic branching programs, called ABPs. And the model of focus for this talk is read once oblivious ABPs. It is a special type of ABP. So it is called read once oblivious ABPs, hence ROABPs. All these representations are compact. So in PIT research area, you will find 2 types of PIT algorithms: white box PIT and black box PIT. So white box PIT, you can see the internal nodes of the representation. So be it circuit, ABP or ROAP, you can see inside the circuit, and while giving a PIT algorithm, you have access to the circuit. In black box PIT, however, it is a bit more difficult. You cannot see inside the circuit, you cannot see inside the ABP, you cannot see inside the ROP, but you can only evaluate the polynomial. So for all of these representations, you can evaluate in polynomial in the size of the circuit or ABP. So you can so it is like Oracle. You can put a field point, give a field point as input, and it will give you the value of that polynomial at that field point. So I hope that it is clear. So what is black box PIT? So black box PIT is defined in terms of what we call hitting set. So let fancy P be a set of polynomials in n variables of degree D. Black box PIT algorithm for P outputs a set of points H. So this is a subset of f to the n, since we have n variables. So tuple, it will be a set of tuples and n tuples. So such that if f belongs to this set or class of polynomials P and it is non-zero, then there will always exist at least one point in our hitting set, which will on which f will evaluate to non-zero. So this f of alpha bar not equal to 0 means that h hits this polynomial. So there will always be one point in the hitting set. So for different polynomials in the class, different points may give non-zero values. Okay. So so first I'll show a very simple example. So univariate polynomials, say of degree d, can we give a hitting set? So we know that for univariates over fields of degree d, it can have at most d roots. So if I pick any d plus 1 distinct points from my field, that will act as my hitting set, because there will always be one point where the polynomial will value to a non-zero polynomial will value to non-zero. If the polynomial is 0, then of course at every field, every point in the hitting set, it will value to 0. So this is a simple example of d plus 1 size hitting set for univariates. So I hope everyone gets a feel of what this black box PIT problem is. So there was a very beautiful PIT lemma in this area, which gives a randomized polynomial time algorithm for black box PIT. So the lemma is as follows. So let f be any unvariate multivariate polynomial, non-zero polynomial of total degree d. So pick any set S, a finite subset of f of our field, and of size strictly greater than degree. Then you pick n points at random from S, and if you evaluate the polynomial at that point alpha 1 to alpha n, its probability of being 0 is very less. So it is d by S. So for example, if I pick my set of size greater than 2d, so this probability is less than equal to half. In other words, probability of in complement probability of this being non-zero is high. It is greater than half. So what is the randomized algorithm? Randomized algorithm, simply I given a polynomial, I pick a random point from this big enough set and evaluate the polynomial at just this single point. The hitting set is just a single point in the case of randomized algorithm, and with very high probability, it will, if the polynomial was non-zero, it will evaluate to non-zero. So this gives a very simple randomized PIT polynomial black box PIT. And if you try to de-randomize this lemma, you can see that you can a trivial de-randomization is d plus 1 to the time to the power n. So picking a so if I pick a set of size greater than d and I take all the points from it, so instead of one random point, if I try to make it deterministic, I will evaluate at every point in S. So S is of size greater than, say, d plus 1, size d plus 1. So for each tuple, each coordinate, I have d plus 1 choices, and there are n such coordinates. So I get d plus 1 to the n time deterministic algorithm for PIT. But this is of course exponential time. So the main goal of this PIT problem in this area is to de-randomize this PIT lemma in polynomial time. Do we have a deterministic polytime algorithm for this problem? So it is a very nice algebraic problem, and it has connections with many other algebraic problems. So for example, lower bounds, it has connection with lower bounds. It was used in an instance of it was used in primality testing of numbers. It has connection with deciding existence of perfect matching in a graph. It was used as in the proof of IP equal to P space. It is also, this problem has equivalence with polynomial factoring also, and it is also used in the polynomial equivalence problem. So you can find the references of each of these results in the paper. I have not stated it here right now. So I'll give a typical standard example of PIT algorithm. So let's see. So univariate was too easy. So let's increase the complexity a little bit. So general PIT is still open, of course, as we are still studying the problem, and it seems difficult as of now. So what the community tries to do is solve for special cases, for restricted cases. So can we get polytime algorithm in those cases? For example, if we have the class of sparse polynomials, So sparse I means that the sparsity or the number of monomials, non-zero monomials in the polynomial is polynomial in the size of the circuit or size of the ABP or size of the ROABP. So such polynomials are called sparse polynomials. So can we, under this promise of low sparsity, can we find a black box, polytime black box PIT? Can we do better than d to the n? So for this, there is a very nice idea. So first, there's a very famous map called Kronecker map. So xi goes to y to the, so you map. So this is a typical PIT algorithm. You give a variable reduction. You go from n variables to say a single variable or constantly many variables. So at the same time, if you ensure, so for example, xi goes to y to the power d to the power I minus 1. So note that each monomial in its exponent form, x1 to the e1, x2 to the power e2, so on, xn to the power en. If individual degree is strictly less than d, so I can view each exponent vector as a d-array number. Okay, so if I apply this map, so I will go from n variables to single variable y, but what will be the degree of the image? It can go up to d to the power n minus 1. So this is still, so this map, because of d-array representation, it will keep each, for different exponent vectors, it will keep its image distinct, because we are taking d to degree strictly less than d. So it will preserve the non-zeroness of polynomial. So if we have two monomials were not cancelling, they will also not cancel after the map. So the problem is that it is still a very high degree, d to the power n, which we were getting anyways. So what Agrawal Biswas 2000, so there are other versions also. So I am presenting this version in 2003. So they use the idea of going modulo prime numbers, modulo a lot of times. So they say, so they prove that there exists a number r, which is at most poly in m and log d. M is sparsity, n is number of variables, and d is degree. So there will exist one number such that if I apply this map and go in the degree, I go modulo this r. If f initially f was 0, after the map also it will be non-zero. If the f was non-zero, after the map also the polynomial will remain non-zero. So we say that sparse PIT map 5 preserves non-zeroness of m sparse and variate degree d polynomial. And now once we have gone to univariate, we can simply evaluate at degree plus 1 many points. And since the degree was polynomial, so we get a polynomial size rating set. So this is a typical example of a PIT. And this sparse PIT is actually used in most of the PIT algorithms. Even in our paper, sparse PIT is used, and you will find this algorithm, routine in many of the PIT algorithms. In fact, most of the hard work is done in the algorithm is in proving why this sparse PIT will work. This is the more difficult. So now we'll talk about the models of interest. Models we'll be discussing. So we won't be discussing the algebraic circuit, but I'll just, for viewers, I'll just give the simple examples. It is a very natural way. There are only addition and multiplication gates, and the computation is done bottom up. So this is one example. So, but we'll move to the more important one for this slide, important model for this slide, called algebraic branching program, ABP. So ABP is defined as a layered directed acyclic graph with a unique source and sink vertex. So edges are going from source and are directed towards the sink. And there's a layer from source, there will be layer 1, then layer 2. So edges are between layer I to layer I plus 1. And the last layer is the sink vertex, single sink vertex. And the edges are given weights as linear polynomials. Okay. So weight of a path from source to sink is defined as product of the weight of the edges. And the model and the polynomial computed by this ABP is sum of all the weighted paths from source to sink. It is a very natural definition. So here there are 3 parameters of size. One is width of the ABP. It is defined as maximum number of vertices in each layer, and then we have the length of the ABP, length of the longest path from source to sink, and we have number of variables. So the edge weights are multivariate linear polynomials. So we'll see one example. So this is our starting vertex source. This is our sink vertex T. The edges are directed from source to sink. So, and the edges, each edge is labeled with some linear polynomial. So there are three paths from source to sink. So if you verify, the first path is computing x1 plus x2 times x1. Second path will actually cancel out the weight of the first path, and we will be left only with the third path, which will be x2 times x3. So this ABP is computing this polynomial x2 times x3. Okay, I hope this is clear. So so this was a graph theoretic representation of ABP. There is also an algebraic representation of ABP called in terms of matrix multiplication of matrices. So I can actually write this. I can write this first layer as row vector, and then this is first vertex. Sorry. So this is first vertex. This is second vertex. So this is 1, 1, x1. This is 1, 2 of this matrix. So there is no edge from the second vertex to first vertex. So this is 0, and there is one x2, which is this x2 entry, and 1, minus 1. So I can actually take out the constant and put it in the form. So U transpose, then product of length of the ABP many matrices, where the initial U, the U and V are just row and column vector, this column vectors. U transpose is a row vector and of field constant, and DI are basically matrices with linear entries as linear polynomials. So this is another useful representation. So another special type of ABP is read once oblivious ABP. So here it is, the structure is, the graph theoretic structure is the same as ABP. There is source and sink, and it is also layered. But here each variable is read only once, hence the name read once. And edge weights are univariate instead of linear polynomials. Now edge weights are univariate polynomials. Okay. And in matrix form, I can write it as U transpose. So D1 x pi 1, D2 x pi 2, so on till Dn x pi n, and multiply again by a column vector of field constants. So this, each variable is only read once. So each variable will appear only in one matrix, and the order in which it appears is given by some permutation pi, which we call the variable order of that ROABP. So a normal example, it can be x1, x2, so on till xn, or x2 time first x2, then x1, and so on xn, and so on till xn. So variable order actually is an important parameter for ROABP. We will see why. So here the size is given by 3 parameters. Called one is width, one is length. Here in this, length will be just the number of variables actually. Each variable is read once. And another parameter, so edge weights have degree D univariates. So degree is also another parameter. So in our paper, actually we will restrict both width and length. So width will be constant and length will be log-variate, logarithmic, but degree will be free. So one parameter is still free, and it so it still is non-trivial. So let's see one example. So this is computing the polynomial x1 plus y1 times x2 plus y2, so on till xn plus yn. So this path is computing x1, this path is computing y1. So from this first node to second node, I am computing x1 plus y1, sum of these two paths, and then I add such gadgets serially. Then the next one will multiply it with x2 plus y2, then x3 plus y3, and so on till xn plus yn. So you can see this is a width 2. So I forgot to tell the width. So here also it was width 2 ABP and length was 3. So now in this ROABP example, width is 2, number of vertices in each layer maximum is 2, and the length is 2n, which is the number of variables, 2n many variables. So here this ROAP is computing this polynomial in the order x1. Then we have the variable y1, then x2, then y2, then x3, y3, then finally xn and yn. So we have a width 2 ROAP in this variable order. But actually one can prove that if I keep, for example, if I take the variable order, if I want an ROAP in the variable order x1, x2, so on. First, I want to exhaust the x1 to x variables, and then I want to start y1, y2, and so on till yn variables. Actually, the width will blow up. It will become 2 raised to n. One can prove that. So this is proved using Nissan's characterization, which we will see next. Okay, so I wanted to give one comparative example, a single example for which I have drawn both all the three things: circuit, ABP, and ROAP. So the example is a bivariate example, x plus y to whole to the power d. So for circuit, we have this addition gate x plus y, and then we do repeated squaring and we compute x plus y whole square, x plus y whole to the power 4, and so on till x plus y to the power d. So number of multiplications gates is log d many. So size of this circuit is also order log d. And then I have an ABP, which is single width 1 ABP. There's only a line. So the source is S, sink is T, and then I have x plus y as edge weights for each of these. So x plus y whole, I have d many such edge weights, and I get x plus y whole to the power d. So it is a d length ABP width 1. And I also have this ROAP for this, which is width d plus 1, x raised per 0 to x to the power d plus 1 width, and the length is 2 bivariate. So the first edge weight is x to the power d, then 1, then x. So this is given by the binomial expansion of x plus y to the power d. Then I have x to the power d minus 1 into d times y, so on, x times d into y to the power d minus 1, and 1 into y to the power. So sum of all these edge weights, all these edge paths, all these weighted paths. So you can see that circuit I could do with only log d size. Then in ABP I had just width 1 and d length. Here I have d plus 1 width. In ROP I have d plus 1 width and length 2. So these are in, so the most expressive is circuit, then ABP, then ROAP. It is in this order. We will not formally prove it, but I will just mention this in this talk. Okay, so as I promised, so how do we, so the beauty of ROAP model is that you can actually exactly characterize the width of a polynomial. So generally for some models, models, we only have lower bounds or upper bounds, but in ROAP he gave a Nissan in 1991 gave a measure which exactly determines the width of a ROAP computing that polynomial. So it is a rank based measure such that a polynomial f is computed by w width ROAP if and only if that measure is less than or equal to w. So it is both sides. This is the beauty of this model. So using this Nissan's this characterization, he actually Nissan showed for non-commutative ABP, but it also applies to ROABPs. Nissan showed that both determinant and permanent have ROAPs of size exactly 2 to the power theta n, exponential size ROAPs in any variable order. So, and Mahajan Vinay in 1997 showed that determinant has an ABP of size order n cube. So determinant is an example which has a polynomial sized ABP, but it has exponential size ROAP. So these the two classes are separated. ROABP is much restricted class. ABPs, lower bounds are still not known. The lower bound problem is still open. And permanent, we believe it to be hard also for ABPs. So determinant is an example which is easy for ABP but hard for ROABP. So okay, so let's now go into the various restrictions we have put on the model. Why we are talking about constant width, log-variate, what is sum of ROABP model. So we will motivate each of these things. Let's see. So PIT for ABPs is still open. Even lower bound is open. Why I say even lower? Because if we solve PIT, that is a result. So ABP is still a hard for the community. So in fact, in 2019 they showed, okay, my net is unstable. They show that even PIT for piece will almost solve general PIT. It will, if you give a polytime PIT algorithm for log width to ABPs, then you give a quasi-polynomial time algorithm for the general problem. So both the number of bits and bits, but the model is ABP. So we will be talking the combined restrictions in case of ROABPs. So solving PIT for ROABPs is the natural first step before attacking the general ABP model. Since exponential lower bounds are already known, as I showed in the last slide, determinant and determinant is hard for ROABPs. And the other example, polytime, we know the exponential lower bounds, but polytime Blackbox PIT, a strict polytime Blackbox PIT is still open. We have quasi-polytime, but we are searching for a proper polytime Blackbox PIT. This is a natural model to attack first. So now let's talk about the log-variate restriction, why it is well motivated. So recently we have a lot of bootstrapping results. So they say that you can PIT for extremely low variate circuits suffice to solve the general PIT. They show AGS showed that if you solve PIT for log constant many compositions of logarithm, log of S variate circuits, size is S of the circuit and variables is extremely low. This log compose C of S. If you solve PIT for this also, then you can solve the general PIT. And this was for this result was for GKKS, Guo, Midmar, Saptarshi, and Noam Solomon. So this, if you save even 1 point in the hitting set, so the general hitting set is D to the N. If you give a hitting set, if you save just one evaluation point from the hitting set, then also you solve the whole PIT problem, just saving 1 point. So this log-variate is well motivated. Another reason is, so was this log-variate model, log-variate restriction ever useful? So was this parameterized algorithm? So what we're doing is, now the problem is hard. We are trying to and saying, can we give a PIT algorithm which is 2 to the power n poly in 2 to the power n and size of the circuit? So in fact, FGS in 18 showed solved the PIT, Blackbox PIT for log-variate sigma power sigma. So sigma power sigma is the famous diagonal depth 3 model. So they were able to give a separate the variable parameter from the size parameter successfully for this model, diagonal depth 3 model. So diagonal depth 3 general variate is still open, but log-variate has been solved successfully. So the next step in the PIT research area can be solving Blackbox PIT for log-variate ROABPs. And in fact, if you solve PIT for log-variate commutative ROABPs, then you solve PIT for general and variate diagonal depth 3 also. So this can be seen using duality trick of Saxena and FSS paper in 2014. So commutative ROABPs means that the underlying algebra of matrices is commutative. For example, diagonal matrices. So the variable order does not matter. If it computes in one variable order, it will also compute in any other variable order. So solving PIT for even this log-variate commutative ROAP will solve the much attacked diagonal depth 3 model. So one thing we should note in the log-variate regime is that the trivial de-randomization d to the power n times actually gives us s to the power log s black box PIT trivially. So we trivially get a quasi-polytime black box PIT. Therefore, using brute force. So therefore, in log-variate regime, we need strictly polytime. So this was the log-variate restriction. Then we can talk about the constant width restriction also. So this model is still open. So GKS attacked this constant width ROAP. They gave a polytime black box PIT, but they had two restrictions. First, they demand that the variable order be known, variable order of the ROABP be known, and the fields over which their algorithm works only for fields of characteristic 0 or very large or sufficiently large characteristic. So just a single constant width ROAP problem is also open. So now we can say we have a restricted constant width also, variables also. So now we talk about the sum of constant width ROAPs. And in fact, it is much stronger, much more expressive than a single constant width ROAP. So for example, KNS in 2016 constructed an explicit polynomial, which is computed by just sum of two width 3 ROAPs, constant width 3, and there is only two summands. But if you want to compute it using a single ROAP, you will require 2 to the n, at least 2 to the n width. So for general variate, it is exponential width, and even for n equal to log variate regime, the width is still super constant. So you cannot compute sum of constant width ROAPs with just a single constant width ROAP. So sum of constant width log variate ROAPs cannot be expressed as a single constant width log variate ROAP. So hence, before our work, there was no polytime PIT known even for sum of two log variate constant width ROAPs. We still only had the best known was just quasi-polytime, which is the brute force one. So we solved this model in our work. So I also want to show connection with other PIT models, which are still open. For example, the one I already mentioned, that PIT for log variate commutative ROAPs implies PIT for diagonal depth 3 model. So we solve for log variate constant width ROAPs in our paper. And another connection is PIT for sum of unbounded-many. Unbounded again means input bounded many. Log variate constant width ROAPs, combined restriction, but sum is unbounded. PIT for that model also implies PIT for diagonal depth 3. So we have shown this connection in the appendix of our paper, but it is the same trick, the duality trick, and together with FSS paper. So this model will solve the diagonal depth 3 model. So in our paper, we solve this model with the restriction that each ROAP is computing a homogeneous polynomial. And then there is another connection. So PIT for sum of general width, general variate ROAPs and unbounded many, input bounded many summands. That model will solve PIT for multilinear depth 3. Multilinear depth 3 PIT sigma pi sigma is still open. So these are few connections. So let me quickly recap the previous results. So I will only talk about selected few results. So first was polytime white box PIT for ROAPs. So in white box the ROAP has a polynomial time algorithm. This was given by Raj Spilka in 2005, or maybe so RS 2005. So white box is done. So but what about black box? So Forbes Spilka in 2013, they first defined the ROAP model properly. RS had given only for non-commutative ABPs, but it also applied for ROAPs. Forbes Spilka defined this ROAP model and gave a quasi-polytime black box PIT. when the variable order is known. And AGKS give the best result till now for general ROAPs, which is quasi-polytime black box PIT in general, no variable order restriction. So and then in GKST 2016, they give a quasi-polytime, the authors give a quasi-polytime black box PIT for sum of constantly many ROAPs. So same as the complexity of a single ROAP. Sorry. And for constant width, as I mentioned earlier, the GKS give polytime black box PIT for constant width ROAPs, but for known variable order and specific field characteristics. Okay. So these were few important results I wanted to touch, which are more connected with our paper. Okay. So now we will be talking about our results. We will quickly see the proof overviews of our result. We will not go into details. So I stated in the first slide, I stated the result informally. Now I'll state it formally. So this is our theorem 1 for sum of ROAPs. So let P be a set of multivariate polynomials and variate polynomials over a field computed by a sum of C many ROAPs, each of width R and size S. So remember, width and number of variables is restricted, but degree is still independent. So degree is unbounded it is bounded only by size. So size, degree is contributing the maximum in the size of the ROAP. So the variable, also the variable, we don't care about the variable order. It is unknown. We are solving the for unknown variable order, not for known variable order. So for this model, black box PIT for P can be solved in this much time complexity: S to the power C and R to the n times 3 to the power C time. So this complexity is polynomial time when our width R, the number of summands ROP C are constant, and n is log S. So S to the C is poly S. So 3 to the power C will be constant for C constant, and R to the power constant to the power log S will be like 2 to the power log S. It will be poly in S. So this complexity will turn out to be poly in S for these restrictions. So as I mentioned earlier, both brute force gives D to the power n time complexity. Since D was D can be as big as S, so we only get S to the power log S time complexity from brute force. And GKST gave result for sum of ROAPs, as we said in the previous slides, for the sum of ROAP general width ROP model, but their algorithm is also quasi-polytime. So it does not help in even under these restrictions. It is still quasi-poly. So we give a polytime algorithm for these restrictions. Okay, and the second theorem is sum of homogeneous ROPs. So now we can tackle we are not restricting number of summands to be constant. C is not constant anymore, but each ROP is computing a homogeneous polynomial. Rest of the model is same. So in this case, we give poly in C times R to the n comma S. So again for so R is for constant width R, and n is log S, and C is arbitrary. So we get a poly S time algorithm. Also note that each ROP is computing a homogeneous polynomial. They may be homogeneous in different degrees. So final polynomial may still be inhomogeneous. Just each summand is computing a homogeneous polynomial. So we will actually first, so proof of theorem 2 is easier, and it will give a lemma which will also be used in proof of theorem 1. So we'll first discuss the second theorem. Okay. So we give two new techniques in this paper. So for theorem 2, second theorem, we use this, we give this technique that syntactic homogeneity can be achieved in same width. So if you, so anyone familiar with the algebraic complexity course or algebraic complexity area, you know there are homogenization theorems. For example, for circuits, we say that if there is a polynomial computed by size S circuit, then there is also a circuit which computes each of the homogeneous degree D for each of the homogeneous parts of the polynomial with a polynomial size blow up only. So in poly-S, you can construct a circuit which computes degree 0 homogeneous part of the polynomial, degree 1 homogeneous part of the polynomial, and so on till degree d homogeneous part of the polynomial parallelly. So we say that if the polynomial computed by an ROAP is homogeneous, you can actually do this homogenization in same width. You don't incur any blow up. So doing this homogenization in same width for a homogeneous polynomial computed by an ROAP will help us solve give us a polytime algorithm. We'll see later how. And for theorem 1, for sum of ROAPs, GKST used log support concentration. They said they gave a weight assignment such that if you shift the variables with that weight assignment, you get log support concentration. So most of the people may not be familiar with this term. We will not go into detail, but it just means that if you shift the polynomial that is computed by sum of ROAPs, after this shift, there will be one, if the input polynomial was non-zero, there will be one monomial with non-zero coefficient, which is of support logarithmic only, log s only, and then you can do brute force and give a s to the power log s time algorithm. So there was this problem of log support. We want to give strictly polytime, so we show how we can bypass this log support concentration route for sum of ROAPs model. So these are the two new techniques in our paper. And of course, many more little lemmas, but broadly, these are the two techniques. So we first talk about the sum of homogeneous ROAPs model. So first I formally define what do I mean by syntactically homogeneous. So I say that ROAP is syntactically homogeneous if for any two nodes u comma v, any two vertices in the ROP u comma v, the polynomial computed from with u as source and v as sink, the polynomial from u to v is homogeneous, and I can pick any two nodes in the ROAP. So such a ROP is called homogeneous. I'll show an example in the next slide, a simple example in the next slide. And we give this structure theorem that if a homogeneous polynomial was being computed by an ROP of width w, then it can also be computed by a syntactically homogeneous ROP of width r, which is less than or equal to w. So I can do this homogenization in the same width. I can construct I have an syntactically homogeneous ROP of width less than or equal to w, less than or equal to w. The only thing was that the original ROP was computing a homogeneous polynomial. Then I can do the syntactic homogeneity. So we prove this is a nice structure theorem. We believe that it has more applications than the ones it provides in our paper. We are still trying to utilize this fully to its potential. So we prove this using the Nissan's characterization, and we use the variable disjointedness property of ROPs, that each layer is just uses only one variable. The next layer is disjoint from the previous layers. So you can cut your ROP at any layer. So there will be a prefix and suffix. So the variables will be disjoint. It is not that, so after the second layer will not have the layers of previous layers, variables of the previous layers. So we using these two properties and a degree argument, we prove the structure theorem. So we will not prove it here, but I'll just give an example, nice example. So remember we had this x plus y to the power d example for circuits, ABPS and ROPs. So I'm just taking the example x plus y whole square. So this is one ROP. I've written it in, this is just a bivariate. So I've just written it in matrix form. I'm not giving a graph version. So you can see this complicated expression. So this is actually width 5, 1, 2, 3, 4, 5. So I am expressing it as this is layer 1 and this is layer 2. This is univariate in x, this is univariate in y. So you can compute x plus y whole square in this form. And the natural representation x plus y whole square, you can also write it as x square times 1 plus 2x times y plus 1 times y square, the simple one. So note that the second one is syntactically homogeneous. Each you pick any two nodes, the the edge weight is just a homogeneous polynomial. So we actually show we will show that if the ROAP is syntactically homogeneous, each edge in the ROAP will just be a univariate monomial, single monomial. It will not be a, so in the first form it is a sum of monomials. It is a polynomial, univariate polynomial, but in syntactically homogeneous you will get single univariate monomials. So a viewer may ask, how did I come up with this very weird representation of complicated expression for x plus y whole square? So actually, if one is familiar with diagonal depth theory, so you can say you can apply. So this is x plus y. Suppose a more general example, x plus y to the whole to the power d. So this is fan in one, top fan in one diagonal depth theory. So the why diagonal depth theory is subsumed by ROAP is using duality trick. So you convert this expression into sum of product of univariates, and you imply this is done using interpolation, and you get this form, which is sum of product of univariates. This is sum of five summands, and this is product of univariates. So this has a actually, so in bivariate you cannot see the diagonal structure. If you have three variables, you can see there will be one middle matrix also, which will be diagonal. So hence the name diagonal ROAP, diagonal depth theory. So diagonal depth theory gives a diagonal ROAP. So the simple point I want to convey is that you get a more width 5 representation of ROAP in this form. And as promised in our structure theorem, there will be a syntactically homogeneous ROAP of width less than equal to W. So here the width is 3, which is less than equal to 5. So this is one example which is just which example for our structure theorem. Okay, I hope this is clear. So now I will give a how this structure theorem helps us in proving theorem 2. So note that if there is syntactic homogeneity, it implies that edge weights are actually monomial. Why? You pick your two vertices from consecutive layers. So edges are between consecutive layers only. So you pick your u from layer I and v from layer I plus 1. So syntactic homogeneity says that it should be the polynomial computed should be homogeneous. So u to v, there is only one edge. So that edge has to be homogeneous. That means, and this edge is in ROP, each edge is univariate polynomial, and making it restricting it to be homogeneous just means that you will be left with just a single monomial. So each edge weight actually you will get a univariate monomial. And so beautiful thing with monomial edge weights is that you will get a sparsity bound on the polynomial, which is r to the n. So to see this, see that the first row, so first row vector is r many monomials. Then you multiply it with the r cross r matrix of second layer. So it will take each entry of this row vector multiplied with matrix will actually blow the sparsity with the r square. So there are first row, this row vector will be multiplied with first column. So and each column is a single monomial. So you will increase the sparsity by r. So initially the starting sparsity was 1. You increase the sparsity by r. When you multiply next layer, you will increase the sparsity by another factor of r. You will get r square. So actually after n layers, with n layers you will get r to the n minus 1. I'm just saying r to the n here. So note that for constant width and log variate, this is polynomial sparsity. So this immediately solves our problem. Why? So we have C many ROAPs, each is computing a homogeneous polynomial. And using our structure theorem, we have proven that each polynomial f1 to fc, each is of sparsity r to the n. So the total sparsity is less than equal to c to the power c times r to the n. So now we can just apply the sparse PIT map and solve it in polynomial time. So note that this now we have given a polytime black box PIT for arbitrary sum of homogeneous ROAPs, and of course the two restriction constant width and log-variate. So we have proved theorem 2 in this way. Side result from this arguments from the structure theorem is that we also give a PIT for a single ROAP of constant width and log-variate. So without homogeneous restriction, there is this single ROAP may be inhomogeneous. So which you can say as a sort of closure result. Let us first see the statement. So let f be a degree D polynomial computed by W. Then I said f of D. So this denotes the degree D homogeneous component of f. So the leading homogeneous component of polynomial will find R less than equal to W. So in a sense, I'm saying that the ROAP model, is closed with respect to leading homogeneous component. That means if the whole polynomial was computed by width W, then its top leading part also be less than equal to W. So this is a nice result. So one may ask this question for other models also. What happens? So like you can show for low partial derivative space dimension polynomials. The same thing holds, that their leading homogeneous component will also be low partial derivative space by the same proof which we have now. So what about other models? Does this hold ABPS? I don't know. I think formulas, we don't. Formulas homogenization theorem is also not okay. Also, why? By structural theorem, we can say now that this the homogeneous top leading homogeneous part FD is also computed by an ROP of width R. Then by our structural theorem, this sparsity will also be less than equal to R to the n. So now we sparse PIT mapping polytime black box PIT for single constant bit ROP. So this hitting set, this black box PIT for single ROP, we will now use for sum of constantly many ROPs, which each ROP can be inhomogeneous. Now homogeneous means, but we will be talking about constant many summons. We had arbitrary many summons. Now we'll be going to constant many summons, removing the homogeneous restriction. We are lifting the homogeneous. So in this case of two ROPs, and this argument can be easily extended to many. So the
Pranav, there seems to be some problem with the connection. Your voice is not coming properly. Um,
hello,
yeah, am I audible?
am I back? Yes. Should
Yeah,
I start again?
yeah, you can start. There seems to be some problem with the audio, I guess.
Okay. Am I audible now, right?
Yes, you're. Um, please try to share your screen again and see if it works.
Is it on?
Yeah.
So I was talking about this sum of two ROAPs model. So the easier case is that both A and B have width R in the same variable order. So you are given two ROAPs, you are given that they have width R. So suppose they had width R and the variable order of A was also the same as variable order of B. Then you can actually simply construct, put these ROPs A and B in parallel and construct a single ROP of width 2R. You put these ROPs in parallel, add a new source, add a new sink, add two edges from this source to the source one of first A, add an edge with to the source of ROP B. Similarly, add edges from A sink to the new sink, B sink to the new sink. So in this way, you actually blow up only linear additively. You blow up the width only additively. So this is an easy case. So the difficult case is that A and B are given have width R and they are given in different variable orders. So what to do in this case? So first understand that sum of ROPs is a non-trivial model because there might be cancellations. So we cannot apply the previous idea because the leading homogeneous components, for example, of A and B might cancel out, and our theorem structure theorem does not the theorem does not hold that intermediate components of the polynomial might not be computed by R. They actually blow up. We have examples for that. So they will become non-constant width. So we cannot apply the previous idea, and they might be because of cancellations. Okay. So what to do when we have different variable orders? So note that the sum of ROP model was first handled by GKST. So I first described their white box idea first. So what they do is that they iteratively build ROABP of B in variable order of A. So layer by layer. So they the variable. Suppose the order of A was x1, x2, so on until xn. So for B they will, and for B it was something different. So first using x1 variable, using this Nissan's characterization, and there is this notion of dependency equations which they define in their paper, and we also used that notion in our paper. So they build for first layer they build an ROAP, then for second layer, and so on. So in this way, if A and B, A was not equal to minus B or A plus B was not 0, there will be okay. Here also there is one easy case. Suppose if I build the ROP for B in the variable order of A, it might be the case that B also, it again is of width less than equal to R in variable order of A also. Then again, in the same way, I can handle this. I can make a 2R width ROP and it can be handled. So the final, after all this pre-processing, we are left with this case 2B, which is difficult. So B does not have width R in variable order of A. Now we have this promise. So, so this means that for case 2B, we will encounter first some layer, some first layer where B will deviate from A. What I mean by deviation is that this deviation is certified. So if A plus B is non-zero, so B will not there will be a first layer where B will not get have width R in that layer. It will, the widths will blow up. So there B will not follow the dependency equations of A. It will not have the same ROAP structure in that layer. So there will be a first layer which will appear. So I am not defining it formally, but conceptually it means like this. So layer by layer you go build the ROP, and there will be first layer where it will not work. And actually in white box, you can actually find this non-zeroness certificate. So this deviation is a certificate for non-zeroness of this polynomial A plus B. And you can find it in polynomial time in white box, because in white box, the variable orders are given. And you can do this process, this step-by-step process in polynomial time. So the problem for black box is that the variable orders are unknown. You don't know the variable order of A. How will you build the ROP of B in this variable order? So what GKST did in their paper was that they took the shift route. So they constructed as I told earlier, they constructed a weight assignment. such that when you shift the polynomial by that weight assignment, it becomes log support concentrated. And that gives actually quasi-polytime algorithm, because that weight assignment, to construct that weight assignment, you need quasi-polytime. And also log support gives quasi-polytime. So quasi-polytime, we know that it is trivial in log-variate regime. We need a strictly polytime algorithm. So what do? We try to search for this certificate of non-zeroness in 2 to the n time. We exploit that we are in the log-variate regime. We have this flexibility of 2 to the n, and using we exploit this to give a polytime algorithm. So the idea is as follows. So suppose B deviates at kth layer first time. So k is in between 1 to n. In a way, we go over all k length prefixes. I mean, suppose the variable order of A was x1, x2, so on till xn. So I go over all k length prefix. I check all the variable orders from x1 to xk. But suppose k might have been the deviation might have occurred at last. It can actually take, in the worst case, it can take n factorial time, because if I have to go through all the permutations of n variables, I have to take n factorial time. N factorial is roughly n to the n, which is super poly, even in when n is log variate, n is log s. So this idea does not work. So we actually, how to do it in 2 to the n time. So we do a small correction. We say that don't go over all the k length prefixes, but go over all k size subsets. So you just guess the variables in the prefix, but you don't care about the order within the prefix. So going over all k size subsets is so k varies from 1 to n. So n choose 0 to n plus n choose 1 plus so on till n choose n, which is less than equal to 2 to the n time, going over all subsets of 1 to n. So this process takes 2 to the n time. And why we don't care about the variable order? So why we just guessing the variables in the prefix is fine with us. We don't care about the variable order within, because we will apply a PIT map of single ROAP on this prefix. And the previous single ROAP map, which we discussed in a few slides before, it is independent of variable order. We don't care about the variable order in that. It worked for all variable orders. The variable order was unknown, so we don't care about the variable order there. So therefore, just guessing which variables appear in the prefix is sufficient. We don't care what is the order within the prefix. So this is how a very high level overview of how we do it in 2 to the n time. We go over the obstruction of variable order in 2 to the power n time. We bypass the log support route and take this direct route of using a hitting set of a single ROAP. So suppose the variable order of A was given by this permutation pi. So I'm saying, suppose variable order, renaming the variables as y1 to n. Okay. So I will apply a PIT map, prefix map. I call it a prefix map on the first. So I guess a k length first k variables on the first k minus 1. So suppose the deviation was at the kth variable, kth layer, yk layer. So first k minus 1 variables, I will map it using a PIT map to a univariate in T1, say T1. Then deviation layer variable, I mean the variable of the layer where since A is not equal to minus B, A plus B is non-zero, there will be a layer by our case 2B. There will be a layer where B will deviate from A. So that variable I will keep as it is. So I guess the first k variables, and I guess this correct yk by going over additional n choices. And the remaining variables, I again map it using a suitable map, PIT map. I call it a suffix map. So yk plus 1 to k yn, I will map again to a univariate in T2, say T2. So I'm going from n variables to trivariate, 3 variables. So once I go to 3 variables, the problem is easy. Constant variables, I go brute force. So now the difficult part is proving why this will work. Why will this preserve the non-zeroness? So we proved that using PIT maps, both phi and psi. If I take these maps to be the fitting set, the PIT map for single ROP of width order R cube. So instead of width R, I have this little below R cube. Then I can actually preserve this non-zeroness certificate. So going from variables n to 3 variables, I can actually say that so A will have a ROP in these 3 variables T1, YK, T2, and preserving this, it means that B not at YK layer, the second layer YK, B will not have the same as that of A. So I will preserve this non-zeroness certificate. So this was the very broad idea of this paper, of this second result. So this R cube, actually this is the factor in our theorem. So there is this term R to the n times 3 to the power C. So this 3 is coming from this. So in GKST, they had in the shift, they said that a shift which worked for a single ROP of width order R squared times D. So there was a degree factor also that will work for sum of constantly many. But here we don't want degree to come into the picture because degree is as big as sizes. We want to remain constant with the gene. So that was also another problem to tackle in our paper. So you say that a single ROP of width order R cube, a PIT map for that will suffice for sum of 2. And similarly, for sum of C, we can do it recursively, and we get this doubly exponential factor of C in the exponent, because recursively I will go R cube, then I will require R to the 9 width, and then R to the 81 width or 27 width, then 81, and so on. So also the thing to notice that our algorithm is not limited to constant width. So what I mean is that here we are getting polytime algorithm because we are using the PIT of a single ROAP as a black box, and we use it to give PIT for sum of C, constantly many. Suppose if we had a polytime PIT algorithm for general width, any super constant width, then also we can extend it to solve PITs for sum of constantly many using our technique, the technique in our second theorem. So it can be, so we give this meta lemma in the conclusion. So our method can be seen as a reduction from PIT of sum of C ROAPs and PIT of single ROP with whatever complexity you have for single ROP. You can multiply it with this factor of C, this double exponential factor of C, and give a similar width ROP. So you need a single ROP of similar width in log-variate, and you need to guess this prefix. You need this 2 to the n. You need this 2 to the n flexibility. So you also need log-variate. So our meta diagram is seen as a reduction from PIT of sum of C ROPs to PIT of single ROP in log-variate setting. And then I will end with few open problems left in this area after in the context of our work. So the following models are open. So the main one is polytime Blackbox PIT for log-variate ROPs, the single log-variate ROPs, even if you have commutative ROPs. So this solves diagonal depth 3 if you solve PIT for this. The next one is polytime Blackbox PIT for, now we in the first one I restricted width. In the second one I'm restricting just, in the first one I restricted number of variables, log-variate. In the second, just the width. So we need PIT, polytime PIT for constant width ROPs, for which work for unknown variable order and all fields. GKS gave it for known variable order and specific fields. And the third one is polytime Blackbox PIT for sum of unbounded-many log-variate constant width ROPs. We had given PIT for this model, but under the restriction that each ROP is computing a homogeneous polynomial. So if we lift the homogeneity restriction, if we solve this, then also actually we solve diagonal depth 3 as I told earlier in the slide. So these are the future open problems for this model. So I think I have ended here. So further are only references. Okay. We can end. I hope I did not take much time.
Yeah, okay. Thank you, Pranav. I think our viewers will definitely appreciate the effort. Thank you so much for the talk.
Thank you for all the patience.
Yeah, To a message to the viewers, if you have any doubts and questions, you can post them in the comment section below. And I hope Pranav will be able to answer those in
Yeah,
some
I
time.
will try to check them daily and
Yeah.
answer
Okay.
all any queries.
Good.
You can share your ideas. I mean, you can share any idea also, any kind of feedback, not just questions, any feedback.
Sure. Sure.
Okay.
Yeah. And yes, the slides as well will be available in the description and on the SIGTAX website. I think that's all. Thank you, Pranav, once again, and
Okay.
stay safe.
Thank you.